Okay, so today we are going to see the basics of bitwise algorithms, and these algorithms are used to perform operations on bit level or to manipulate the bits in different ways. So, and also it is used to improve the efficiency of program. If we see the example to check if a number is even or odd, we can use this. So, in general, what we do, suppose we have taken an example a is equal to 5. If you want to check if it is a even number, so what we do, 5% to we'll check this one. If it is 0, that means it is a even number, and if it is not, that if it is 0, then it's even number, and if it is not, uh, then we say it is a odd number, right? So here what we can use is we will check the last bit of that number. So if I write find binary form, so it's 101. So the last bit is 1. So it is what? It is odd. If it is supposed to 6. So if we write 110, it's 6. So it's even. We need to check only the last bit, and if it is 1, then it's odd. If it is 0, then it's even. So this is the example. Next we are seeing the bitwise operators. So there are total 6 operators which we are going to see. The first one is AND. uh, so AND, for example, if we take A is equal to 5 and B is equal to 3, so we have to find A and B. So while doing the AND operation, we have to consider these rules that if there are two bits, we are doing the AND operation of that two bits, suppose, and any of them is zero, then the answer of the and operation of those two will be zero. So here, so what will be one, if any of, suppose one is one, another one is zero, then the answer is zero. If it is zero and one, then also it's zero. If it is zero zero, then also it is zero. If it is one and one, then only the output will be one. So here, if I represent it in the binary 0 1 1, so both 1 0 is present, so the output here is 0, here is 0, and here is 1. So A and B equal to 1. So the next operator is OR operator. If we see A is equal, if we take again the same example, A or B, we have to find. So in using the while using OR operator, we have to see if any of them is one, any of two. I mean, we are in two bits, right? We are comparing these two bits. So any of them is one, then the answer is one. So here 1 0 1 0 1 1. So any of them is one. So answer is 1 1 1, as each two. I mean the each pair of two bits contains one, at least one time. So the answer of A or B it's what, 7. So if we have seen the AND operation and OR operation. So here if you see A and B is 1, A or B is 7. What we got? The same thing. Now the next operator is what? Bitwise XOR operator. So yeah, A XOR B, we have to find it. So while doing the XOR, what we have to remember is if both the bits are same, then the answer is 0. If the both the bits are different, then its output is 1. So for example, it's 1 0, then the output will be 1. If it is 0 0, output is 0. If it is 1 1, it output is 0. So here if we are finding the XOR, the same example we'll consider again. Both are different to 1, both are different to 1, both are same to 0. So what is the answer? It's 6. So here you can see AX or B is 6. Next is left shift and the right shift. So shifts we are going to see. Suppose we are given the same number, suppose A is equal to 5. We have to do the left shift operation on this. What, how we will do? A left shift, this is the sign of the left shift. By how many times? I mean, suppose x. X can be anything. So for example, I want to do by 1. So what is 5? It's 101. So if I do the left shift of 5, is we have to just shift the bits to the left side by 1. So here it's 1010. We'll get this one. Because we can write this 101 as this. If we consider the 8-bit number, then this is the binary representation of the 5. So if we do the left shift by 1, what we will get? Yeah, we'll get this thing. So what is this? In decimal, it's 10. So left shift A by 1, 5 by 1, the output is, that is 5, left shift by 1. So what we'll get? We'll get 10. Similarly for right shift, if we do the right shift, 5, right shift by 1, what we'll get? So here 0, 0, 0, 1, 0, 1. So if we do the right shift, 0, 0, again 1, 0, and then 1, 0. This one, we are doing the right shift, so we are removing this thing and adding the front to 0 to the front. Okay. So this is what we get, and what is it? It's 2. So this is the left shift and this is the right shift. These two operators we have seen. We have to shift the bits just either to left, either to right, and we have to consider this is either 8-bit or 16-bit, whatever the bits you are considering. The next operator is bitwise NOT. So here also we'll take the same example. A is equal to 5. So A is equal to 5. So we're doing not. So not means inverting or flipping all the bits of the digit of the binary. So here we have 101, right? 5. So we'll flip it. So as before only I said that this this is the 8-bit representation of this decimal 5. So we'll flip the digit bits of this. So it's 010. So here we got this as our not of a, right? But uh, this is a negative number as okay. So how we find the it is a negative or positive number? So we'll check the first bit of this binary. So if the first bit is 0, that means it is a positive number, and if it is 1, then that means it is a negative number. So here we can say this is a negative number, and for a negative number we can directly convert binary to I mean decimal by using some technique. Here what we do, we find the 2's complement. We find the 2's complement, and we'll get the decimal of that negative number. So what is 2's complement? First we do, we flip all the bits and we'll add 1 to it. So flipping all the bits will get, hmm, okay, yes, the same string, same binary which before was. Then now we'll add 1 to it. So 1 also we can write in this form. Yeah, we are adding 1 to it. So what we'll get is 1 plus 1. 1 plus 1 is 2, and we represent 2 in the binary as 1 0. So carry, we'll get carry as 1, and write we'll write it here the 0 and carry as 1. Again this carry plus this 2. 0 plus 0 is 0, plus 1 is carry. Oh, sorry, is 1. Carry plus 1, I mean the carry plus 0, carry is 1, so 1 plus 0 is 1. And again this 1 plus 0 is 1, so we'll get 1. And the rest all are 0, so we can ignore this, or we can write the 0 also. But what we are getting, the answer is 110, that is it's a 6. Yeah, and it's a negative number, so what we write, uh, not of a equal to negative 6, I mean minus 6. So this is the answer. So in this way we use the bitwise not operator, and we have seen this different bitwise operators. Now we'll see some facts about bitwise operators. So we can't use the left shift and right shift operator for the negative numbers. And also, okay, so here what we got, here we considered 5, right? So left shift of 5 by 1 is 10. So we can also use this, I mean, we can map, I mean, understand, just understand what I'm trying to say. Like, if we are using the left shift, then we can also I mean, map this with the multiplication or division. So we'll do multiplication by 2 if it is a left shift, and not by only 2, 2 power, suppose here 2 power x, we have to multiply 2 power x to the initial number 5 star 2 power x. So here we are doing the left shift, right? That's why we are multiplying. Otherwise, we have to divide. So multiplying what x we have considered 1. So it's 2 power 1 is 2. That means 5 into 1, sorry, 5 into 2 is 10. So the same answer we got. If you are doing the right shift, then we have to divide by 2. So yeah, here what we'll do, 5 divided by 2 power x. So x is 1, so 5 divided by 2 is 2. We'll take the integer value, right? So while dividing, so it's 2, so we got the same answer. So we are it's a these are equivalent to multiplication, division by 2 respectively, and it's on 2 powers x, whatever x we are considering. And the next is, yeah, this and operator can be used to quickly check if a number is odd or even. We already seen this example in the beginning only. And yeah. And also here what is used, that x and 1. So initially what I told, that if it is here it's 1, then it's odd. If it is 0, then it's even. Also, instead of checking the last digit directly, what we use for and operation. So here if it takes 0 0 1, this is the 1. If we do and this with this, so we know if one bit is 0, that means the output is 0, right? Of this 2, and of this 2 will be 0, this 2 will be 0. So if I'm using 1, if I'm considering one number, I mean the 1, so we are checking the last digit. So if the last digit is 1, then the answer will be 1. So 1 and 1 will be 1. If the last digit is 0, that means the answer will be, will get total 0, as we have already here all zeros. This all zeros will lead to the 0 only, and again here 1 0, so 0. So if we will do and operation with 1. So if I want to check the number a is even or not, I'll do and with 1. So if it is 0, that means it is a even number, and if it is 1, that means it is a odd number. Yeah. And also for doing this all operation, we need only o of 1 time complexity. So we are doing just the and, or, XOR, left shift, right shift. For doing this one operation, will O of one is will be the time complexity. Yeah, this is the basics of bitwise algorithms. Thank you.